Okay, so welcome to everybody. This is our third day of the conference in honor of our friend Claudio Bartocci. So the first speaker of today will be Nicolò Sibilla from SISSA, who is going to talk about Fukaya category of surfaces and Pant's decomposition.
Yeah, so thank you very much. It's a pleasure and an honor to speak at this conference for the 60th birthday of Claudio. My first contact with Claudio was through a marvelous book that he translated called The Elegant Universe by Brian Greene when I was in high school. Certainly, one of the big motivations that persuaded me to study mathematics, and I think I'm not alone in this experience. Really a wonderful book that documents an amazing interaction between mathematics and physics, the shape of mathematics in the last 30 years. Then Claudio was a teacher of mine, a professor at the University of Genova. And I remember, maybe this anecdote is apocryphal. It's not that funny, but I use it to make a point. So I remember going to Claudio and saying, Professor Bartocci, it'd be wonderful if you could teach us about the mathematics of string theory. And I remember saying, but we are doing string theory. And he literally was teaching us connections on vector bundles. So it's a long way away somehow from the frontier. But what was very important to me and shaped my taste and my career in mathematics so far was this very, very broad horizon of Claudio. This was very exciting. You know, instead of framing mathematics as a very narrow, specialistic subject, he had this broad outlook that made you feel that everything was connected. I think this is very much one aspect of the mathematical taste and career of Claudio, and had a huge impact on me. In the last few years, we have become, I hope I can say, close friends. So for all these reasons, it's really a great pleasure to speak at this event. Okay, so I apologize. I think I've given this talk, well, new results sort of, I tack on new result, but the first 10 minutes, I've given this talk like 100 times. So if you were at some other talk I gave, you will know how this will start. So Pant's decompositions and HMS and homological mirror symmetry for surfaces. So what I'd like to do is I will start with a survey of homological mirror symmetry for Riemann surfaces. I should say this is all joint. There are 3 papers. The last one is from the summer with James Paskalev. We've been working on this for almost 10 years. And our understanding has become more complete, as I'll explain. There is one crucial piece that we understood last year, and that again we return on the paper that we posted on the archive this summer. So for Riemann surfaces, from the perspective of what I call shift theoretic methods. So and then I will explain our more recent work. So as I said, in these 2 preprints, one from last year and one from the summer, on compact Riemann surfaces. So I want to start from a very simple example of homological mirror symmetry. I will not even say what is homological mirror symmetry. It will be apparent from this example. This is a version of homological mirror symmetry for P1, so for the projective line. And this is a marvelous idea of Bondal So let me say after Bondal, Fangelio, Truman, Zaslow, and others. Okay, let me just say homological mirror symmetry in general, is a mysterious duality that pairs up two spaces. Pairs up two spaces that are mirror partners and tells us that algebra geometric information on the first space corresponds to symplectic information on the second space. And this is exactly, homological mirror symmetry is a version of this. So the first category, so what I write down is a series of categories and equivalences between them. And when we compose all these equivalences, we will have a homological mirror symmetry statement. So the first category belongs to the world of algebraic geometry, and is the derived category of P1. So this has made an appearance in Hugo's talk. You should think of this as a category whose objects are some enhancement of coherent sheaves on P1. The second category belongs to the world of representation theory, and is the category of representations of the so-called Kronecker quiver. Now, I should say that all my categories are triangulated, DG enhanced, but this is not so important for us. What does it mean, representations of this quiver? Well, this is something very simple. So objects in this category are essentially two vector spaces, V and W, and two linear maps between them. And then I'm taking the derived category. Now, this equivalence here is a beautiful, famous result of Bellinson from the end of the 70s. And is the first result in which basically really showed that the derived category wasn't just a construct that was useful, so for theoretical construction, it's something that could be computed and contained a lot of information on the varieties themselves. The third category belongs to the world of topology, and is the category of constructible sheaves on S1 stratified by a point. So what does it mean? Well, here we are looking at sheaves of, say, complex vector spaces on S1 that have the property that they are constant when restricted to the point and to the complement. Okay, so this also is a triangulated category. And also this equivalence is part of a beautiful and complex story. This is part of the so-called exit path. Sorry. Exit path formalism, which was initiated by McPherson. Okay, let me say both equivalences are by fairly, this is completely elementary. So what you should think is that a constructible sheaf here has basically only two interesting stocks, which is the stock at this point and the stock on any other point away from this mark point. And these two stocks will be these two vector spaces, making up the quiver representations. Finally, the fourth category belongs to the world of symplectic geometry. And this is the Fukaya category of the cotangent bundle of S1 relative to lambda. And I'll explain what lambda is in a second. So this equivalence is again a much more recent, but a beautiful result of Nadler-Zaslow. I think from 2006. And that was very influential in sort of shaping the study of the Fukaya category in the non-compact setting in the last 15 years. So let me state the theorem of Nadler-Zaslow theorem. Sorry, before doing that, let me make a comment. As I said, when we compose these equivalences, we get an equivalence between the derived category of P1 and a Fukaya category of T star S1 relative to this decoration. So this is telling me P1 is mirror to T star S1. Okay, algebra geometric information on P1, the derived category, is matched by the Fukaya category of T star S1. I even said, and I don't have the time or the competence really to define rigorously the Fukaya category in this setting. The Fukaya category is an invariant of a symplectic manifold. Cotangent bundle is a symplectic manifold thanks to the Liouville symplectic form. Is an invariant of symplectic manifolds, which is a very sort of complicated invariant, but roughly objects in the Fukaya category are Lagrangians in the cotangent bundle, and Holmes compute the, let me just say, the quantum intersection theory of Lagrangians. The Fukaya category is a categorification of quantum cohomology for people that are familiar with that object. So, so the theorem on Nadler-Zaslow says the following: let M be an analytic manifold. Let lambda containing T star M be a conical Lagrangian. So what does it mean conical? It just means that it's invariant under the dilation, fiber-wise dilation on the cotangent bundle. So the action of the positive reals by dilation on the fiber. Then there is an equivalence between the Fukaya category of T star M lambda and the category of constructible sheaves on M with singular support in lambda. I'll make a comment on this in a second. So in the case we discussed, so first let me specialize to the case we discussed. So in the case we discussed, so for which plays a role in homological mirror symmetry for P1, what we had is that lambda was given by the following shape. So first of all, the cotangent bundle of S1, of course, is just a cylinder. And lambda is the union of the zero section and the cotangent fiber at the marked point. So this is T star S1. So the comment I want to make is that if we have a stratification of M, which is the most standard context, now when we look at constructible sheaves relative to stratification, well, we can express this via singular support just by taking the conormals of the strata. That's what we did here. Okay, so this category, where M is S1 and lambda is this conical Lagrangian, is the same by definition as constructible sheaves on S1 with respect to this stratification. Okay, but in this way we can describe more general categories of constructible sheaves where we have something which is slightly weaker than a stratification. Okay, so and this was the last equivalent. So as I said, derived category, Fukaya category. So an instance of homological mirror symmetry. So what's important and sort of astonishing in this theorem is that an object which is, as I said, notoriously complicated to calculate, like the Fukaya category, gets reduced to an object, the category of constructible sheaves, which is in nature topological combinatorial, highly computable. Okay, so sheaf theoretic methods in the Fukaya category, in the study of the Fukaya category, and here there is a long list of contributors to this line of thought. So this circle of ideas: Nadler-Zaslow, then Nadler, Kontsevich, Dikroff, Kapranov, let's say ... and then GPS, so Ganatra, Pardon, Schende, which are really building up the foundations in a very systematic way. So sheaf theoretic methods in the study of the Fukaya category, aim to generalize this picture given by the Nadel's-Zaslow theorem to manifolds such as the following. So let me draw it for you. This is a torus with 2 points removed, and I'm drawing the points removed as these two boundary components. And then I'm drawing what we call a skeleton inside. I'll explain in a second. So let me call it gamma. So this is an exact symplectic manifold. What does it mean, exact symplectic manifold? It means that the symplectic form is a boundary, so it's d theta, where theta is a one form, and that's a key property of cotangent bundles. This is exact symplectic manifold. However, which is not globally a cotangent bundle. So it shares a property of cotangent bundle, is in a precise sense locally symplectomorphic to a cotangent bundle. However, it's not globally a cotangent bundle. It has some global geometry. And here's the idea. The idea is the following. So if X, and I'm being a bit vague because one would need to specify some more assumptions. So, but if X is such a symplectic manifold, so for us, let's think exact. We can equip it with a skeleton and the Fukaya category, will localize on the skeleton. I'll explain what I mean in a second. First, let me explain what a skeleton is. I've drawn an example here. So for us, we should be a bit more careful, but for us, it's just a Lagrangian that sits inside my symplectic manifold as a deformation retract, like in this case. Okay, so what does it mean that the Fukaya category localizes on the skeleton? Well, that is a sheaf on the skeleton. So let me write it. So that is there exists, so there exists a co-sheaf. Let's not worry about the difference between sheaf and co-sheaf, but say a sheaf of categories over the skeleton gamma, having the following two properties, such that, so one, the global sections of gamma compute the Fukaya category of X, and two, the local section of F are computable. So locally, F of U is equivalent to some, say, category of constructible sheaves and those will be further expressible as representations of a quiver, category of representations of a quiver. So the point is that F globally computes something that we really want to calculate, but is very difficult to compute, the Fukaya category. But locally, as this very simple shape, it's just the category of quiver representations. It just depends, it's easily computable from the topology of the skeleton. Let me make a remark that connects this sort of general program to the case of cotangent bundle we discussed at the beginning, which is encoded in the, which is given by the Nadler-Zaslow theorem. So if X is equal to T star M and gamma containing T star M is conical, okay, is a conical skeleton, then we are saying that there should exist a natural sheaf of categories MSH, this stands for microlocal sheaves, on gamma, on the skeleton, on this conical Lagrangian gamma, such that its global sections are equivalent to constructible sheaves on N with singular support, in gamma. And indeed, in the theory of constructible sheaves, this is known. So this is the so-called, it's a very important construction, this is the so-called Kashiwara-Shapira microlocalization. So basically, the point is that we can spread a category of constructible sheaves over the whole cotangent, not just on the base, but over the whole cotangent bundle. In particular, if we fix a conical Lagrangian as singular support, we can spread it to be localized over the whole gamma. Okay, so let's specialize. As I said, the case we're really interested in is very simple topologically. I mean, we're just interested in Riemann surfaces. So when X is a punctured, so non-compact Riemann surface, understanding this sheaf of categories, understanding F reduces to something quite simple. Indeed, basically, so let me first write it and then motivate it. So we can always assume that we have chosen as a skeleton for a Riemann surface a trivalent graph. So if you allow me, I'll just quickly scroll back and show you. This was a 4-valent graph, but we can just choose another skeleton, which instead is 3-valent. And trivalent skeleta are generic. Okay, so we can always do that. So let's assume that our skeleton, and this of course holds for any Riemann surface of any genus, any number of punctures. No, we can always choose a skeleton which is trivalent. But then the local shape is always just this. I mean, the skeleton maybe is some complicated global geometry, depending on the genus and the number of punctures, but locally it looks like a trivalent graph. So in order to explain what is the behavior of this sheaf, I need to tell you what are the sections of this sheaf on such a trivalent vertex. And the answer is that this is the derived category of representations of this quiver. And then I need to explain to you what are the three restrictions. I mean, this is a sheaf. I can restrict it to the three legs. And this is sort of very simple. Let me decorate this with a typical object in this category. So V, W related by a linear map F. And then the three restrictions are what you imagine. So they all go to, let me write it, perf K, so vector spaces. So the first restriction is the restriction on the first vector space V. The second just maps this representation to W. And the third one maps this representation to the cone of F, okay, which is a convex in general. But okay, and so now if I explain myself so far, if what I said is clear, then you know, I'm just trying to understand the sheaf, but the sheaf by definition is something that I understand completely once I understand its behavior on the basis of open subset. And so this is what I just done. And so in principle, this ansatz, this proposal that I presented says, okay, now you have done this, you have understood this sort of very simple local picture. Now you're able to compute the Fukaya category of any puncture-driven surface. Okay, this is indeed the case, and this point of view gives easy proofs of homological mirror symmetry for punctured curves. Now, this is something that I worked on by now many years ago, 10 years ago. Many other people have contributed. Let me give you first a simple example. Try to convince you that the ideas are really simple. So again, B side is the algebraic side of mirror symmetry. A side is the symplectic side. So on the B side, we take the following nodal curve, just the arithmetic genus one nodal curve. Now, the mirror of this, and there are various ways to motivate it, for instance, based on the SYZ picture of mirror symmetry, is a puncture torus with one puncture. The number of punctures matches the number of nodes, it's dual to the number of nodes. And here I'm going to decorate it with this skeleton. Okay, the fact that this is Lagrangian is obvious for dimensional reason. Any curve on a surface, on a symplectic surface, is Lagrangian. And the fact that it's a deformation retract, I think you can also see it. So what we want to compare is the category of perfect complexes over X. Sorry, it could be the derived category of X, but I'm choosing this formalism. Perfect complexes are just literally vector bundles on X and complexes of vector bundles. This is different from the derived category only if X is non-smooth, as is the case here. So I want to compare this category with the Fukaya category of X wedge. Okay, and so what I'm going to do is that I'm going to express both categories in terms of simpler categories that I understand better. So perf X turns out to be an equalizer of categories, and sorry, like this. I'll explain what this is in a second. dB co point. And this is I0 upper star, and this is I infinity upper star. Okay, so what am I saying? Okay, what's an equalizer of category? Well, there is a formalism to make sense of that, but we think of an equalizer in ordinary category theory. Here we need to be a bit more careful because this is strictly speaking what is called a homotopy equalizer, but no matter. The meaning of this statement is really very simple. What we are saying is the following. Giving a vector bundle on X is the same thing as giving a vector bundle on its normalization P1, together with identifications of the fibers of this vector bundle at 0 and infinity. This is a completely geometric and standard, or at least intuitive statement. No, we can, if we have a vector bundle here, we pull it back to P1. And to reconstruct V, well, we need to remember how I glue together the fibers at 0 at infinity, which get identified in X. When I formalize this, this gives me this equalizer of categories. Now, the Fukaya category is in turn the global sections of a sheaf, and more precisely is given by the following equalizer. So let me show you what I mean. So these are open, these guys are just open subsets of the skeleton. So I'm just taking an open cover of the skeleton that looks like this, and then say this, okay, and these two open subset of the skeleton is not exactly what I'm going to do, but you know, I'm doing something very similar. I'm rather self-gluing, but that doesn't matter. I'm rather self-gluing this bit of the skeleton. Anyways, what I'm trying to, the point here is that the reason why I can write the Fukaya category as this equalizer is that, as we said, the Fukaya category is a sheaf. And now, the point is that these categories are equivalent. This is this homological mirror symmetry for P1 that we started off with. No? Remember, we exactly compared the dry category of P1 to a certain category of constructible sheaves that depended on lambda, and lambda had exactly this shape. On the other hand, the equivalence between these categories is trivial. Okay, we're just saying that the Fukaya category, the sheaf on just an interval is given by the category of vector spaces. Therefore, we conclude that these two categories must be equivalent. And now this is much less trivial, but it follows, drops out sort of automatically from these formalisms. So there are many generalizations. To puncture curves of genus 1 are mirror to stacking model curves of genus 1. There's work of Sibilla Zaslow, is Kontsevich had proposed this, then many other people, Dikerov Kapranov, Lekili Polishuk, more recently generalized it to higher genus, and then in higher dimension, there's work of Gamage and Schende.
Nicolò.
See? Yes.
Could you give us a simple idea of what the two maps in the Fukaya equalizer are?
Yes. So yes. Absolutely. So let's do it. So the point here is that f of this piece of the skeleton is simple. F of this piece of the skeleton is basically by construction the same as constructible sheaves on a swan stratified by a point. I mean, this is the formalism that says when you are on a portion of the skeleton that looks like a conical Lagrangian in a cotangent bundle,
yeah,
apply Nadler-Zaslow. So now this is representations of this quiver. And again, this is completely, can be made completely explicit. So if you want more details, I can give more explanations on these equivalents. But once you have this model for this category, the two restrictions are given by taking the cone of F and the cone of G. So an object here is given by V, F, G, W, and you need to send it in two different ways to vector species. And you do that by sending V, F, G, W. This guy gets sent one of the functor will send it to cone of f in perf k, and the other functor will send it to cone of g in perf k. And then it's just a matter of checking that once we identify this variability with this, these cones correspond exactly to taking the pullback at 0 and infinity.
Thank you.
So that then this is a commutative sort of diagram of diagrams of categories. So then what it turns out that the Fukaya category, that Fuk, in the exact setting, so this was by now very well understood, sorry, but then something new sort of we realized that as also a different type of local to global behavior. And now this is let me give you a formulation of this theorem, which is not for many reasons optimal, but this is by myself and Paskalev. And so suppose that we have sigma. Sigma is a puncture Riemann surface, gamma is a skeleton. And so suppose that we have two closed subskeleton. Such that they are a closed cover of gamma, so such that gamma 1 union gamma 2 is gamma. And then there is also a condition that their intersection is a disjoint union of S1s. This is not quite enough. I'll explain the right condition. Then f of gamma is the following fiber product of categories: f of gamma 1, f of gamma 2, f of gamma 1 intersecting gamma 2. So actually, you'll see this has a very specific geometric meaning that I'll highlight in a second. Let me just say that the correct condition that we want this gamma 1 and gamma 2 to satisfy is rather that where they overlap, where they intersect, they look like this. So as I said, the condition is that they'll intersect at an S1. So this is the S1 they share, and they lie on the two sides of the S1. This is a very, I think, transparent geometric consequence that I'll explain in a second. But before, I want to revisit homological mirror symmetry for P1 from I mean, this is a simple example, of course, but from what is really a completely different perspective. But the technique is always the same. So we break down the categories that we are interested in into simpler categories. So on the B side, we have the following. So we have, I apologize, I'll write perf just because I'm used to write perf, but just dB core, because this is all smooth. So this is so again, we'll write perf P1 in a very simple way as a fiber product of categories. This fiber product of categories encodes a very simple geometric property of P1, namely the fact that is covered by two, it has, if you want, a toric affine open cover given by two copies of A1 that meet, that overlap in a GM. And so it's no surprise, and once you have the right formalism, this is really trivial, that giving an object here is the same as giving an object on the two open patches together with an identification on the overlap. And this is just formalized by saying that perf P1 is this equalizer. On the other hand, on this side, here we have F of this shape. And thanks to the thanks to the theorem that I just stated, we can you see decompose this shape into this top part and this lower part and intersecting in S1. They satisfy exactly the assumptions that I need. And then the statement is that actually all these categories, and I will not go into the details, but believe me, I mean, these are trivially equivalent. This is really a triviality. And this is trivially equivalent to this. But then this implies that the two categories that we are really interested in are also equivalent, because they are both fiber products of the same diagram. No? These long horizontal arrows are telling me this diagram of categories is exactly equivalent to this diagram of categories. And so then somehow the most important corollary of that statement, which was proved by us and independently with very different method by Heather Lee, is the following. If sigma is a different kind of local to global behavior of the Fukaya category, if sigma is a punctured Riemann surface with a Pence decomposition P, I remind you what this is in a second, then the Fukaya category of sigma is equivalent to some limit of categories P in big P, for the Fukaya category of P, small p. So let me explain what this means. First, let me box this, and then let me explain what I mean. Basically, what's a Pence decomposition? Something like this. So this is a genus 1 curve with 3 points removed, and I'm decomposing it in pieces that look like this. And so this is what we call a perp Pence. And so what this theorem is telling me, and as I said, this is a different kind of local to global behavior. The Fukaya category of this thing, I understand it completely once I understand just the Fukaya category of one very specific Riemann surface, the simplest, almost the simplest of all. That is the Pence. So now an immediate consequence of this is the key point here that I have to stress in case I won't have a lot of time to explain it, is that this behavior persists in the compact setting. So let me first make comment on this because it's really the key. Somehow is what our more recent work explores. So the other local to global mechanism that I described depends on the existence of a skeleton, but we have no skeleton if we have a compact symplectic manifold. We don't have a Lagrangian over which the manifold will retract. So there is no hope to export this kind of local to global behavior to the compact setting. However, also in the compact setting, also in the compact setting, we can still have pants decomposition, and we do have them if the genus is greater or equal to 2. And so our theorem is that the Fukaya category of a compact surface is no more complicated than the Fukaya category of a puncture-Riemann surface, provided, again, the genus is at least 2, because it's, again, just expressible by a limit of pieces that we understand very well, which are the Fukaya category of the pair of pants. Okay, so an immediate application of this theorem here in the punctured setting is so-called what I call classical Hori-Vafa homological mirror symmetry. It was studied by many people. So this is Oru, Abu Zaid, Efimov, Katsarkov, Orlov, Gross, Katsarkov, Rudat, Buckland, many contributions. And here's the way this works. Is a mirror symmetry in a toric setting, very beautiful toric setting. So we have a B side and an A side. And then on the B side, remember it's always the algebraic side, we have the following. So we have a polytope P, a lattice polytope P, let me say 2D polytope P. Then there are higher dimension generalization, but 2D polytope P equipped with a triangulation T. So, see an example. For instance, this is a polytope in a 2D lattice, and then say I choose this triangulation, a unimodular triangulation. Okay, so this means that there are no interior lattice points, and there are no lattice points on the edges either. So then, what I can do is that we can take a cone over this, and this yields a 3D fan. A fan of a toric Calabi-Yau threefold, which is necessarily non-compact. Otherwise, of course, compact toric varieties are not Calabi-Yau, but this is not a complete fan, which is furthermore equipped with a superpotential to C. I'll comment on this data in a second. And the B-side category that we are supposed to use here is not the derived category of the threefold itself that I denoted X sigma, but rather the relative version of the derived category. So the category of matrix factorizations of W. So when we have a non-trivial map to A1, we have this sort of relative version of the derived category. So what does it mean taking a cone is that we put this lattice at height 1 in a 3D lattice. Then we can take the cone over all these triangles. This gives me a collection of 3D simplices, which is Fn. Okay, and then I can take the toric variety corresponding to it. So the mirror is really, again, there are various deep justification of why this is the right recipe, but let me just restrict myself to the recipe itself. Constructing the mirror is really simple. We take basically sort of a tropical curve, which is dual to this shape. So the mirror of this, in this case, is the puncture Riemann curve whose tropicalization is the dual of the triangulation. So in this case, this is a genus 0 curve with 4 points removed. And then the expected statement, let me call this sigma, maybe, well, I call the fan 3D fan sigma. Let's call this, well, S. Let me call it S W. I didn't say it, but the reason why part of this data is also this, we have this map, is because this fan, the fan that I obtain, has a height function down to R, and historically induces such a regular function. And so, okay, so this is the theorem that one expects in the setting, and the claim is that this immediately follows from, so let me just say it, so this follows immediately from the following two statements. So the first one, the key is this, let me just call it descent by pants for the Fukaya category, descent by pants. And the second one is just the local equivalence, which is the one that says that matrix factorizations. So the simplest example, matrix factorization of XYZ is equivalent to the Fukaya category of the pair of pants itself. Okay, so once we prove this local equivalence, which is very easy, and we have this descent by pants on the Fukaya category, we easily deduce this global statement. Okay, so I have, I think, only 5 minutes, and I want to give you a sense of how the compact case is treated. So, and again, the idea of what we do in the compact case is really very, very simple. So, so the statement, so the theorem is this. So sigma compact, or it doesn't matter because now this is a universal statement. So equipped with a pants decomposition big P, then the Fukaya category of sigma is equivalent to the limit of the Fukaya category of the individual pants. So all these categories are the same because just Fukaya category of the pants, but then we take a limit over all the Fukaya category, over the Fukaya category of the pants making up this decomposition. Okay, so how do we go about proving it? Well, the actual proof is delicate, as I could imagine, on several accounts, but the basic idea is really very simple. So let's do it in the case of a curve of genus 2 equipped with this pants decomposition. Okay, so let's consider sort of a tropicalization. It's really the dual intersection complex of this Pence decomposition. No, just some one-dimensional shadow. Okay, and let's take an infinite cover of this. Well, not quite the universal cover, but the universal abelian cover. So what do I mean by this? I mean that this is, by the usual sort of Galois theory of coverings, this is, so let's call this G. This is the cover corresponding to the quotient of pi1G, which is just the free group on two elements. Well, the quotient from this to its abelianization. Okay, so this gives me this cover. And a way to visualize it is just the infinite tessellation of the plane. And now I take a fiber product here. And what I get here is this infinite dimensional, non-finite type, infinite genus Riemann surface. Looks like this. You can imagine sort of sitting over the plane with infinite genus. No, I hope the picture of what this looks like is clear. Now, the point here is the following. Okay, we prefer to study sigma tilde rather than sigma. As I said, what I'm going to give you is not the complete argument, of course, but the moral argument is this. We prefer actually studying sigma tilde, although sigma tilde is infinite genus, is easier than sigma. And why is it easier than sigma? Because since it's a non-compact Riemann surface, it's actually Stein. So although it's a non-finite type, it falls within the province of these shift theoretic techniques that I mentioned at the beginning. And so in particular, the first statement is that the Fukaya category of sigma tilde is a big limit of the Fukaya categories of the Pence making up the Pence decomposition of sigma tilde. Note that from this Pence decomposition, sigma tilde inherits a Pence decomposition made up, of course, by countably many Pence. So this is still true. One needs to be careful, but this is still true. And then the second statement, so let me call here O pi, the so-called group of deck transformations, no? So the Galois. So then the second statement is that this is used all the time in symplectic geometry. Well, this group acts on the Fukaya category of sigma tilde. And basically, the quotient of this category by this action, categorically, one does the opposite thing. Actually, one says the fixed points, but it's the same story. I can explain why. So, but morally, the quotient of this category by this action is the Fukaya category of sigma. But then this immediately implies that the Fukaya category of sigma is itself expressible as a limit of the Fukaya category of the Pence making up the composition, the Pence decomposition we started with. So, and I'll finish with some corollaries of this theorem. There are many corollaries. So basically, all previous HMS results for Riemann surfaces. These are are beautiful results of Seidel on the genus two curves and Efimov. In general, very complicated or relatively complicated techniques. They are all demystified by this result. So this equivalence is a sort of it's a sort of a homological mirror symmetry machine. We can immediately, if we are given a potential mirror, which in this sort of setting will always be a matrix factorization categories, there is something that is algorithmically computable that will tell us, yeah, this is equivalent to that category matrix factorization. Whereas these earlier results depended on a careful sort of generators and relations sort of proof. So very complicated and really depended on doing some heavy duty calculations. Then there is a statement that says that all brains in the Fukaya category of sigma are geometric. So although the Fukaya category is made up of things that are in principle, say, complexes of Lagrangians, in the punctual setting, thanks to work of Haydn, Kontsevich, and Katsakov, we knew that all these complexes of Lagrangians are actually represented by one Lagrangian. They are geometric, one Lagrangian with a local system. And they asked whether this was true in the compact setting. This follows from our theorem. And then let me just say generalizations. This is also sort of an interesting story. Generalizations of Ori-Vafa to all toric varieties, So Ori-Vafa was a statement about toric Calabi-Yau varieties, so in particular non-compact toric varieties, but there is a story that one can tell in future variety. Okay, I'll stop here because I think the time is up. Sorry, let me just say, buon compleanno, Claudio.
Okay, so thanks a lot, Nicolò.
Maybe I can stop sharing.
There is any question, any remark? Claudio, you are mute.
Because yesterday, so I have two questions, very silly questions as usual. Sorry. The first one is the following. So you said that the Fukaya category is obtained as a limit of Fukaya category of band, but I cannot figure out how the direct system is formed.
Yes,
you need a direct system.
Yeah, so let's do it in the case of. Do you see the share? Sorry. Do you see something? Yeah.
Yes.
Okay. Let's do it in the case of just. You're right. Let's do it in this case. What I didn't say is that it's not just pens, but also overlaps of pens. So the overlaps of pens are cylinders, symplectic cylinders.
Yeah.
So
okay.
So this is Fuk. Let's call this P1, P2. Is Fuk P1, Fuk P2, and then we'll have both this restriction to Fuk of this
cylinder.
Yeah. And the statement is that this is a Fermi problem.
Okay. And the second question is the following one, but just because of my ignorance of the topic, I guess. So starting on the B side, you have the derived category or perf complexes, as you like, in the smooth case. And on the other side, you have the Fukaya category. Of course, you can take cohomology. So on the B side, you have a very highly computable objects, namely Chow rings. And on the A side, you must have something which is less easily computable, I guess. So maybe some kind of quantum cohomology or something like that. I don't know.
Yeah.
So I would like to know if your theorem allows for computing, say, some symplectic invariants previously uncomputable, or something like that.
Yeah. So first of all, I should say that I'm not an expert of this decategorification step, but what you're asking is, I have an equivalence of two categories. I can apply the Hochschild cohomology, no?
Whatever cohomology you like. So.
Right, on both sides. No doubt. So the Hochschild cohomology of the Fukaya category in the non-compact setting is called symplectic cohomology, and so indeed there is something that you can transfer from one side to the other. But I should say that on the B side you have this. Well, yeah, you have these matrix factorization categories, and of course they have a computable Hochschild cohomology in terms of what is called the Jacobian ring. So basically, some ring made out of the partial the partial derivatives of the superpotential. And so, yeah.
If you stop at the, say, the intermediate level, so if you stop on the B side at the K theory,
yes,
you can stop at, there is, I guess, something analogous on the A side.
Absolutely, yeah, absolutely. I'm not aware of a description of the K theory of the Fukaya category. You know, of course, it's a category, so you can take the K theory. It's a triangulated category, you can take it. I don't know what kind of enumerative invariance it contains. It's a very interesting question. Yeah, I just don't know. Yeah, but no doubt, you know, the equivalence of categories, of course, specializes, as you are suggesting, to all these invariants. I guess the thing that I'm not really able to point to is an example in which this transfer of information from A to B or from B to A, which was so important to launch this whole program, no? Via calculation of global Witten theory via periods, as something so interesting to tell us in the settings that I've explained. You see what I'm saying, Claudia? I don't know if there is something.
Yes.
I think that Nicolò frozen.
Frozen, yes.
Yeah.
Or is thinking very hard about K theory.
Okay, so I'm not sure. Maybe we should just move on. So there is any other question? Well, maybe it's not really possible to ask other question now. So let's thank Nicolò. Right. Okay, so maybe we should, I don't know, let me ask to Valeriano. Valeriano, should we somehow stop?
2 minutes.
Yeah, okay, let's have a 2 minutes break. I stop the recording now and can resume.
Okay, excuse me.